Hello everyone, welcome to lecture 10 for drone systems and control course. This lecture consists introduction to control systems. So, this is the first lecture in module 4 which is drone control systems. In this particular module, we will go through understanding and explaining the fundamentals of control systems and their role in drone operations. We will differentiate between open loop and closed loop control systems, specifically with applications in UAVs, analyze the dynamic behavior and system response of drones using time domain methods specifically. Then we will talk about feedback control strategies to achieve stability and some of the performance metrics, desired performance metrics. Then modeling of drone control systems using mathematical tools such as differential equations, transfer functions, state space representations. Then there will be some evaluation metrics for drone control systems such as stability, transient response, steady state error, robustness, etc. We will talk on designing and simulating basic control algorithms, as an example PID controller for real time drone operations, and also there will be some brief discussion on autopilot design for drones. So, with that I will start this present lecture, lecture 10. After this lecture, the students will be able to understand the function of automatic control. We will differentiate it with manual control. Then they will learn representation of control system, explaining the difference between an open loop and closed loop control system. Then there will be a brief idea given on negative and positive feedback, basic idea of stability and the other performance metrics of control systems. Finally, throughout the lecture there will be some examples on drone control. So, why to study control systems? It is an integral tool in modern automation which is found in applications like aircraft, industrial robotics, climate control and more. Presently it is coming in a huge way in drone autonomy also. It enables precision, safety, stability, efficiency and automation. And the concept or broader concepts of control system engineering is very much relevant in different engineering disciplines like electrical, mechanical, aerospace, etc. Okay. So, when we talk about control systems in drones, what we want to control? So, I will give some basic examples that what we want to control, then I will go into much deeper notion. Okay. So, one aspect is attitude and orientation control, whose purpose is to maintain and change the drone's angle, roll, pitch and yaw. You know these angles because you have already gone through some previous lectures. So, roll, pitch and yaw defines the orientation of the drone in space. There are components or sensors like IMU and gyroscopes and accelerometers which provide real time orientation data, angular velocity and acceleration. So, typically there are some control designs called PID control or adaptive control to correct orientation based on these sensor feedbacks. Okay. There is another aspect called altitude control, where a drone wants to maintain a specific height or perform some smooth ascent or descent. So, for that the useful sensors are barometers, ultrasonic sensors or leaders, and PID control adjusts the motor thrust to reach to a certain height or maintain a target altitude. Okay. Then there are some usefulness of control in position and navigation control of drones, where the purpose is to guide the drone to a specific coordinate or location and travel through a desired path or defined path. The inputs or the sensor inputs come from GPS, magnetometer, etc. and control techniques which are adapted here are weapon navigation, path following control using proportional navigation or some nonlinear guidance laws. Okay. One very important aspect of control system is to maintain stability in the system. So, in our lecture or in our course, the system is always the drone. So, stability is required to counteract disturbances like wind gusts, then some dynamical change in payloads, and this is required to maintain the stability. There are certain techniques used here as fast response feedback loops that adjust motor speeds in milliseconds, so that the stability can be adjusted in a good way when there are sudden disturbances like wind gusts or payload changes. Okay. There is another aspect called velocity control. The purpose is to maintain or adjust the drone's speed in horizontal and vertical direction, and speed controllers using feed forward or feedback mechanisms are useful in having or achieving velocity control. Okay. One very important aspect which will be covered in the next module called drone navigation is obstacle avoidance and path planning, where the purpose is to ensure safe navigation by avoiding obstacles. So, in this particular scenario, the drone should start from a particular location and it should reach the goal location by avoiding some static or dynamic obstacles inside the environment. So, the drone should start from this point and should avoid these obstacles and reach the goal location. This is the objective of obstacle avoidance and path planning, and what we call it as a safe navigation which is required. The sensors are LiDAR cameras, ultrasonic sensors, sometimes radars, and the control algorithms which are used in general are artificial potential field, model predictive control, then some reactive obstacle avoidance scenario, control barrier function, etc. We will be covering these topics in the later lectures. So, I am not going into much deeper notion at present. Some other control system aspects in drones are payload stabilization, which you can go through. Then there is something called mission management, where efficiently managing the power consumption is required, and notification of low battery should come. So, for that control logic is used as power budgeting algorithms and then feedback on current draw and battery charge. So, with this mission can be like success of the mission can be defined in a much efficient way. Okay. There are concepts like autonomous landing and takeoff, which has become very phenomenal in like last few years, where the purpose is to safely execute launch and recovery procedures. Okay. Finally, I will talk about formation control, which is again a very important aspect of control systems in drone, where the purpose is to enable multiple drones to move forming a specific formation or specific pattern, where the drones can move like forming a square kind of formation, or it can be something else like a star. So, these things are possible in formation control, and here it should be enabled that the multiple drones execute this particular mission without having inter-agent collision, and at the same time they should avoid collisions in the environment with static and dynamic obstacles, whatever it may be in the situation. So, the control methods which are used here are consensus algorithms, distributed control based mechanisms, and some leader follower techniques. Okay. So, what is a control system? We are talking about drone control. We can control altitude, we can control attitude, maybe stability we can enhance, then we can achieve obstacle avoidance, accurate path planning, all these things we are talking about, and we are telling that control system will help in all these scenarios. But what is a control? What is control system? A control system is a device or set of devices that manages, commands or directs or regulates the behavior of other systems or devices. Okay. So, what is a system? A system is a process or a device that performs an operation on a signal to produce a new signal. So, we have a system like this, I am just drawing it as a box. So, this is the system. What this system does? It will take some signal and produce a new signal. So, the first signal is say S1, when it passes through the system, then it becomes some signal S2. Okay. So, it is an entity that processes input signal to generate output signal. So, we can tell that what we are talking about S1, S1 is kind of okay. S1 is the signal which is the input signal, and S2 is the signal which is the output. So, in this way the system works between input and output signal. Fine. Now, what is signal? A signal is a function that conveys some information like speech signal, like image signal, video signal, something like that, which conveys some information about the behavior or attributes of some phenomenon. It is a time dependent function representing a physical quantity varying with time, space or other independent variable. It uses, so what is happening in control system is that it uses the input signals to introduce output behavior of the system. So, if we have the system in our hand like this, and if we give a specific signal S1 and we need some signal S1 star out of it, then we can check that what is the system behavior, whether it is giving us the desired signal S1 star or it is not giving. If it is not giving, then we need control system to modify this particular system or tune this system, original system in such a way that S1 being one input signal, we get the desired output signal S1 star. Fine. Okay. So, what is the objective? We want to get a desired output or a desired system behavior. Fine. What are the basic elements of control system? Basic elements of control system is there will be system, an interconnection of components to achieve desired function. So, it may not be a single system, it can be some interconnected systems working like this, capital S1, capital S2, these are the systems. Input is the external stimulus or command which is given from outside, which is say we represent as a small s1. Output is another signal which should be a desired signal, but in general we represent it as something called S2. And what is process or plant? Plant or process is the main system whose behavior is under consideration, the part of the system that performs the action. So, in our case it will be the drone or which is called the process or plant, and with some desired, with some input signal or command, it should work in a desired fashion. That is the objective of a control system. Okay. So, in the case of drones, the control system components are like motors, propellers, speed controllers, etc. We give some input signal command, and what we are getting out of it should be a signal which is desired by us. We do not want anything undesired here. That is the objective of control system. Okay. Now, we differentiate between manual and automatic control. A manual control is dependent on human decision making and actions, but when it comes to automatic control, the system can by its own self perform tasks autonomously. So, it does not need any human intervention while performing some action or task. So, automatic systems or autonomous systems reduce human error and improve efficiency. Okay. So, I will give one example of operation of human in the loop drone, where the multi-rotor drone is being operated by a human pilot using a remote control. Okay. The signals which are the input commands to the particular drone or process is joystick signals for changing direction, giving throttle and yaw, something like that. The feedback is that the pilot is visually observing the drone, that whether it is functioning in a desired way or not. So, the feedback is coming from the pilot, and when he senses that something is undesired, then he changes the input from the joystick signals, then he brings the drone to such a condition where it acts in a desired manner. So, the action is that pilot continuously adjusts inputs to stabilize and navigate the drone. Okay. The key characteristics are entire flight relies on human perception and reaction. The precision depends on pilot skill. If the pilot is not skilled enough to do all these activities, then the drone might crash. It is not safe for the operation, the mission may not be completed. So, all these things will be coming here. Okay. So, there will be no built-in autonomous decision making. What the pilot decides is final for the drone. Okay. And also because of all these reasons, its usage is also restricted, and it is common in recreational drones or manual training flights. However, when it comes to autonomous drones, we see that the multi-rotor drone has one onboard autopilot, which like takes the role of the pilot. The controller will be there in the autopilot, like flight control softwares will be uploaded in the autopilot. This autopilot will be functioning in a desired way when there is some input like predefined mission or GPS coordinates where the drone is desired to go, then the onboard autopilot can work independently without any human intervention, and it can take the drone to that particular location. If speed control is required, the autopilot should be able to do that. If some attitude orientation is required to maintain, then the autopilot would help in that. If it requires any altitude hold, the autopilot should be sufficient for that, but you see that there is no manual intervention. Okay. The actions will be drone like when the autopilot is getting feedback from the sensors, then the drone or the autopilot adjusts the flight path, speed and altitude automatically, okay, based on the sensor feedbacks, yeah, of course. So, the key characteristics are that it uses feedback and onboard algorithms. Onboard is important because that is what it makes things autonomous. Okay. It can detect and avoid obstacles because the sensors will give the essence that in the environment some obstacles are present, then the autopilot with proper algorithm will be able to avoid the obstacles, then it will follow the path, land autonomously, reach the desired position autonomously. It operates with minimal or no human intervention, that I have already told, and it is common in many applications, or it is going to be common in next few decades in a even more extensive way in delivery, inspection, agriculture, surveillance, logistics and whatnot. Okay. So, the control system, we understood what it is and what is expected from it. Control system will help the system or process or plant to behave in a desired fashion with some input command. Okay. Now, there are some broader categories of control systems. One is open loop system, another is closed loop system. What is happening in open loop? You can see this particular figure where there is one input signal and we are getting some output signal, like one example of toaster. When the manual toaster, the item is getting heated, there is no control that when it should stop, so the item can get burnt. There is no correction mechanism into open loop. You give some input, you get something out of that particular system components. Okay. Now, what happens? We can't control the system always in a I would say in a desired fashion, and then whatever output signal we get might not be the desired output. So, for that, to add some correction mechanism, there is a concept of feedback. You see this figure, figure 2, where the control action depends on the output. So, what kind of control will be taking place in this particular figure depends on the feedback system. You can find one example as thermostat and read independently to understand what are the differences. So, closed loop systems use feedback to improve performance and accuracy. I will show in the consecutive slides that how feedback becomes important in control systems, autonomous control systems. Yes. So, when we talk about open loop and closed loop systems, there are certain features like feedback. In open loop there is no feedback, and in closed loop feedback is present in this loop. So, this particular feedback system actually closes the loop, that is why it becomes a closed loop control system. Accuracy in open loop it will be low because we do not know that whether finally we are going to get the desired output signal. We do not have any control on that. Okay. For closed loop system, automatically that chance of getting accuracy is high, but yeah, because of this particular loop having sensors into the system, the total cost of the system will go high. So, closed loop system is high in price. Complexity, yes, since some other systems are being added in the system for sensing the environment, checking the difference between the feedback signal and input signal and all this. So, there are certain complexity in the particular or complexity in the total system. Okay. And stability. So, stability, what is stability will be defined in some lectures today, or maybe in some lectures which will be coming later. But the concept is that when we put some input or input command, then whatever we get out of that should be one bounded signal. Okay. So, we will come to these concepts of bounded signal, bounded input or bounded output signal, stability later. So, what I want to conclude here is that for open loop, since there is no controlling mechanism and there is no option, whatever output we get we have to accept it, it might not be unstable, but the stability can be improved by using the closed loop system. So, we can see here that adding a feedback loop into the control system, first it was open loop, then we add feedback, which is very important. Okay. Once we add this feedback, we can see that the system becomes a closed loop system, the loop is complete now. What advantage we are getting? We are getting high accuracy, we are getting better stability, but at the same time we have to pay some price in terms of cost and complexity. Okay. There are some examples of open loop and closed loop systems. In the case of drones, one example is like pre-timed takeoff sequence, where the drone is programmed to increase motor speed, say for 5 seconds to take off. Okay. The controller, it is an open loop system, the controller executes a fixed sequence without sensing the actual lift. Input will be some command like spin motors at 70% power for 5 seconds, that is what it is required. So, that input will come, but we do not have any feedback here. So, drone cannot check whether it has lifted off or not. Okay. The output will be that the drone may or may not achieve the desired altitude depending on the battery level, payload, wind. No internal mechanism of feedback is there to check all these intricate details. So, the characteristics of open loop systems is that here the no sensors or measurements are used, since there is no feedback, cannot correct disturbances or errors. Yes, simple, open loop control system is simple, but inaccurate, unreliable, sometimes it can give rise to unstable system. Okay. On the contrary, when we get another example as attitude hold mode with feedback loop, the drone maintains a constant. So, the expectation is that the drone maintains a constant altitude using barometer and range sensor or range sensor. Okay. Now, you see the sensor comes into picture. So, when the sensor is there, there will be a feedback loop, because the sensor will give some output signal and that can be fed back into to check its difference with the reference signal, and accordingly the controller starts working, so that it continuously monitors actual altitude and adjusts the motor speed. So, now there is a mechanism of correction, we know what is happening. If it is not happening in a desired fashion, the controller will work for that, because now it has a sensor data. Okay. So, sensor measures are coming, what it will tell is what is the current altitude. Based on that, if the current altitude is h and we want to achieve some altitude capital H, then the controller will work in that fashion, so that this particular altitude is achieved. So, there can be some controllers we can design as PID control, which increases or decreases thrust based on the error, and accordingly the control action will tell that how much correction is required, that correction will be made, and since we are using feedback, error will be reduced. So, what is the error? Error is the height h minus the current altitude, that will be reduced time to time. Then it corrects environmental changes like wind, battery drain, etc. That means disturbances, whatever comes into its way, that can be handled in a better way, and it ensures accurate and stable altitude maintenance. What desired performance we want out of the system or drone, Based on that, we have to design the controller in such a way that we get the desired performance or performance as much close as that. Okay. There is another example where we talk about fixed yaw turn. The drone is commanded to rotate clockwise for exactly 2 seconds at a fixed motor differential, but you see there are no sensor. Okay. The controller sends a preset signal to yaw motors without sensing actual rotation. Sensor is not there. So, the input command will go like rotate at some speed x for 2 seconds, no feedback. So, the output will be some the actual yaw angle what will be achieved may differ depending on disturbances, inertia, payload, etc. In open loop system, it assumes that the environment is ideal, which is not the scenario actually. No correction is given. So, if the drone is over rotated or under rotated, we can't do anything. It is open loop, so we do not have any control on that. Not suitable for precise navigation or alignment tasks. Fine. Okay. Now, when we see the open loop systems for yaw turn, we check the closed loop version, what can happen here. So, now it is heading hold or GPS weapon navigation. The drone is commanded to face exactly 90° east. So, that is the desired performance we are looking for, and the onboard sensors are there who will give the feedback. The drone then compares current heading with the target or with the desired heading and adjusts the yaw motors. Okay. What is the input? Input is kind of the same desired heading, something is given. Here I am giving an example of 90°. So, the controller, what the controller will do, we can design a PID controller which will correct any deviation to maintain or reach the exact heading, that is 90°. So, that is the usefulness of using controller. When we talk about closed loop control systems, it actively corrects disturbances, maintains precise orientation essential for waypoint missions and stable navigation. We will see that for safety also and for some other performance metrics also, going for closed loop systems is better, though it increases cost and complexity into the system. It is better to go for closed loop system because we have a correction mechanism, and end of the day what we want is some desired performance out of the system. So, in open loop, if it is not possible, then the best solution with complexity and price comes is closed loop control system. Okay. So, now you understand what is feedback control system. Feedback is a process of taking a portion of the output and returning it to the input. Okay. So, this path is actually the feedback path. It is called feedback path, which completes a feedback loop. Fine. What it is doing? It is taking a portion of output and returning it to the input. We do not know how many sensors are there in a particular system. So, all sensors we are putting as one box only. There can be multiple sensors. So, this takes the output and gives back to the input. Input sometimes is called reference input or reference signal, and there is a summer where it is checked that how much difference is coming between the input signal R and the feedback signal say H. Okay. That is called error. The idea is that this error should be minimized. Fine. So, the controller will work for the error and minimize it, so that now a more precise command of input goes to actuator and the drone finally gives the output much closer to the desired output. So, in this way the correction mechanism goes on. The system here compares the actual output to the desired output. Then if there is a difference, it is corrected here. Okay. So, it is used to correct errors, stabilize systems and improve the response of the system. Error is calculated here and is used by the controller to make adjustments so that the error can be minimized. The key components of modern control systems are in that way: controller, then actuator, which are the motors for drone propellers, then drone is the main system or plant, and when we talk about sensors, these are the feedback elements. Fine. So, what are the advantages of using feedback control? It improves accuracy, reduces error, stabilizes the system, compensates for disturbances and uncertainties, enhances dynamic response. What does that mean? Sometimes we need the system to work in a faster way, sometimes we want it to work like function in a speed which is very much application specific. So, we want these things out of the system by using the feedback control. So, what is being done here? I want to summarize this one. When we are getting some output because of the input R, we are feeding back that output through sensors, or the sensors are measuring the outputs and then it is feeding or comparing with the input so that we can compute the error. When we know the error or when the controller gets to know about the error, it tries to minimize it. Based on that, some precise command is given to the actuator and accordingly the drone functions. Okay. There are certain potential drawbacks. The system can become unstable if not desired properly. Okay. So, how we are designing the feedback mechanism, what are the controllers we are using, based on that sometimes the system can become unstable. So, we have to be careful in control system design. Just only putting one controller is not sufficient, or just using some sensors blindly is also not useful. So, we have to be very much application specific. Another potential drawback for feedback control is that it is complex in designing. Sometimes you have to tune the controller in such a way that it can minimize the error properly. So, that is another potential drawback. And as I have told previously also, that when you are using feedback with some additional systems, comparison, etc., the cost and complexity of the system will go high. Okay. But still, when we are getting stable, more accurate and precise performance from the system, we have to go for feedback systems or feedback loop in the control system. Yeah. So, the feedback in drone systems are having following components. One is set point or reference input, which I was mentioning as RT. Then there will be sensors, there will be error calculation. The error is calculated as desired altitude minus measured altitude when it is a kind of altitude control system for drone. Okay. Then there will be a controller which we are here we are just giving an example of PID controller that uses this error to compute necessary throttle adjustment for the motors. So, in that way, in every run, once the controller uses this error, then gives necessary precise throttle adjustment command to the motors, then accordingly the drone will function in some way. We will again check that whether the output is desired output or not, error will be computed, again the controller will give the command to the actuator in that way. So, the motors increase or decrease the thrust accordingly to move the drone up or down in a altitude control or altitude hold action. Okay. Then finally, what we get is the system response, where the drone's altitude changes and the new altitude is again fed back into the system for continuous correction. So, just doing the correction for only one time might not be sufficient. So, when we are getting this reference signal and it is coming to the controller, then the controller is working on the error, giving the command to the actuator to increase or decrease the throttle, then accordingly the motors increase and decrease the thrust. Then finally, the drone will take some altitude, will check the output. If the output is fine, it is okay, it will be checked from the sensors. If we see that altitude is not enough, again it is fed back here and we keep on doing this. Okay. Unless the desired output, that is the altitude, we design it or denote it as capital H. Until this H is achieved, this correction mechanism will go on. Okay. So, why feedback is crucial? I have already told in previous slides that it maintains stable altitude here in spite of having disturbances like wind gusts and all. It compensates payload changes. Just assume that there are multiple payloads carried by the drone, you drop one, then there will be some distribution change in the weight. So, once the payload changes, then the dynamic of the system will also change. So, the feedback system should be able to compensate this kind of changes. It ensures smooth and accurate flight, enables autonomous behavior. So, it is expected that when there is a payload change or there is a wind gust, then the human operator will not go every time to take care of the drone. It is autonomously capable of taking its own care and performing in a desired fashion. Okay. That is the bottom line of autonomous control. Okay. There are some other feedback examples in drones which we are not discussing here, but you can go through the reading materials. These are attitude stabilization using IMU sensors. Attitude stabilization means pitch, row and yaw stabilization. Then there are obstacle avoidance using real distance measurements. Then there are position holding using GPS feedback, something like this. Okay. So, now we are more or less familiar about what are the basic elements of feedback loop. We know that there should be a reference input which is the desired output value. We have a controller CS that determines necessary control action based on the error, right. Then there will be some actuator which converts the control signal is this particular signal, say small c, then actuator converts it into a physical action, like the motor will now take the action to rotate the propellers in a proper fashion or in the specific speed, so that the drone can take desired altitude in the altitude hold example. Okay. So, the plant, what is the plant here? Plant is drone. Sensor, it measures the actual output. So, it is the like integral component of the feedback loop, and it completes the feedback path which compares the actual output with the reference. Okay. So, this is what we are getting, this is called actual output and this is the reference input which is equal to the desired output value. So, the comparison between these two will go on, fine. Okay. Now, there are two different kind of feedback mechanism. One is negative feedback. Negative feedback subtracts a portion of the output from the input and it works to minimize error and stabilize the system. Okay. So, this is negative feedback. When the feedback signal comes here and is getting subtracted from the reference input or desired output, then it is called a negative feedback system. Okay. So, it reduces sensitivity to disturbances and parameter variations, any change in parameters negative feedback can handle. It improves stability, accuracy, it can slow down system response sometimes because it will be covered in the transient analysis lecture, that why sometimes it can be slowed down, but it reduces gain but increases robustness. Okay. So, we are not going into all the details that how negative feedback can do this particular can perform this kind of functions or actions, but it is expected that the readers will go through the reading materials and understand all these things. But we are giving the kind of points so that it becomes clear that what is important in control system design of drones. Okay. There is another concept called positive feedback. So, here the positive feedback actually not subtracts, but adds a portion of the output to the input. Sometimes it amplifies the errors and tends to destabilize the system. Okay. Why do we need then positive feedback? There are some utilities in a very application specific way, because it can increase the gain and sensitivity, but yeah, at the cost of stability. So, it depends on what kind of application we are looking for. So, though it can lead to oscillations or some runaway conditions, it has certain like advantages of increasing gain and sensitivity. However, I would say that using positive feedback is very rare in drone operations. So, we are not giving much time on this. Negative feedback can reduce error, it can enhance stability, can decrease gain, but it is better in altitude or attitude control. Okay. Similarly, when it comes to positive feedback, it amplifies the error. Often it can give rise to instability, but in some applications where increasing gain is required, it can give some help. However, it is rare in drone operations and not used that frequently. Okay. So, negative feedback is the fundamental for safe and stable drone operations. However, positive feedback must be used with caution and it should be in specialized applications. If we are not having caution in implementing positive feedback, then this particular problems can happen. Fine. Now, what is system response? System response is like it describes the behavior of the system over time when it is accepting one input, some input signal or input command. It shows that how the system reacts over time with that particular input. Now, it is important to analyze transient and steady state behavior. Okay. Fine. When it we have what is transient behavior and what is steady state behavior will be covered in the next lecture itself. What we want to do here is that there are certain types of inputs which are commonly used for analysis. So, one is step input. What is that? The step input looks like this. If we plot a step input, say this is t and this is time t equal to 0, then step input is a constant magnitude input which goes like this. Okay. Impulse input is something like this. If it is plotted, it comes for a very short duration of time. Okay. Very short duration input, ideally it comes as a spike. Okay. Then ramp input works like this, it varies linearly with time, and sinusoidal input all of you are familiar about, it is something like this. Okay. Now, what we want to check in system response? It is checking the behavior of the systems when it is subjected to this kind of inputs like step input, impulse input and so on. So, when we give step input to the system, the response is called step response. Fine. When we talk about impulse, then it becomes impulse response. These are very important concepts in control systems and signals and systems. So, accordingly we check the response which is coming out of the step input. If it is not desired, then we have to design the controller in a specific way. Okay. And it is same for all the inputs. Okay. What are the importance of system response in control systems? It can understanding the system response can help us designing the controller in a specific way, so that it can enhance stability, it can give faster response, it can give more accurate response, and sometimes we can design the controller in such a way that it can enhance the robustness. That means, it can handle the external disturbances well. Okay. Fine. Now, one very basic concept which is relevant in control system is that how we have talked about systems. Systems are some basic blocks or interconnections of multiple entities which takes some input and gives rise to the output. Okay. How to represent those systems? We have talked about signals like step signal, ramp signal, impulse like this. Then systems are those entities which will take those signals and give some response. But how do we represent those systems? We have certain input and we will get some output. But when we talk about the system itself, how to define it mathematically? we can define it in terms of differential equations in continuous time. We can denote them as or represent them as a difference equation when it is a distributed a discrete time representation. What is happening here is that, say, u is the control input. So, this is dut dt, that means the derivative of the input, and this is mth order derivative, and here it is like kind of the linear combination of all the derivatives from 0th to nth order, and it is a representation of the system that if we get input as ut, input is ut and output as yt, okay, then how we represent the system is like this. If it is a discrete system, then the same system can be represented as the second equation. Okay. Then there is one very important concept called transfer function. For that we need to understand what is the Laplace domain representation. It expresses the systems in like as a ratio of output to input in the Laplace domain. What is the advantage? You see, when we are talking about discrete differential equations or difference equations, it is in a I want to put it like this. It is we get it as a differential equation. When we do transfer function, we get it as an algebraic equation, and it becomes mathematically easier to analyze the system. Okay. Fine. So, there is another representation called state space representation, and it will also be clear in some later lectures. It will be covered in details, and we will see that how we can like use differential equation or transfer function, and then how we can define the system in terms of state space representation. Okay. So, that is something we will be covering later. So, as of now we should understand that when we have some input and we get output from the system can be represented as a mathematical form as a differential equation or a transfer function or state space representation. Some other representations are also possible, which we are not covering here. Okay. For further reading, you should refer to this particular book by K. Ogata. It will give great details about all these concepts. Okay. Now, it comes to stability. What do we mean by stability? The stability refers to system's ability to produce a bounded output for any bounded input. If we are giving unbounded input to the system, we can't expect always that the controller will be such efficient so that it will give bounded output all the time, but that is the design mechanism. We have to design the controller in such a way that it gives the desired performance. But when it comes to stability, first we have to check that whether we are giving bounded input to the system or not. A stable system returns to equilibrium when it is disturbed from its normal condition. Okay. Instability leads to oscillating behavior or diverging behavior. Just think of a situation where the drone should be taking off from this particular height and or maybe from ground at height h equal to 0, and it should have a altitude hold at height h equal to capital H. Now, if the drone is a stable drone, it will take off, it will come to this height and will hold the altitude at this particular height or altitude. However, if it is not a stable drone, or if the controller is not giving the stability aspect to the drone, then what might happen is that the drone will come to this height and then will start going up or then coming down, something like this. So, this kind of nature, if it happens for some duration of time, it becomes an oscillatory kind of response, which is not a stable response, and hence it is not desirable. Okay. A system is stable if it does not diverge over time and settles to a finite value. We want the system or the drone to come from this particular height and reach here and hold the altitude. However, it is not stopping here and the altitude is getting higher and higher. That is a kind of diverging over time, not desirable. Okay. So, this concept of stability is critical for safe and predictable operation. There are certain types of stability. One is bounded input, bounded output stability. If every bounded input leads to a bounded output, then we tell that the system is BIBO stable. Okay. It is common in frequency domain and transfer function analysis. We will not be discussing frequency domain in this particular course, but the readers are always encouraged to go through the reading materials to understand it. It is a very important concept and will give a different understanding or notion about control systems. Okay. Fine. There is another stability concept called asymptotic stability, where the system returns to equilibrium after a distance. So, in due course of time, the system will come back to its equilibrium position from the disturbed position. Okay. It requires transient behaviors to decay to 0 over time. It will be clear in the lecture of transient analysis what does it mean. Okay. Next comes marginal stability. Output remains bounded, but does not decay to 0. That means there is a some kind of oscillatory mechanism or oscillatory response. What example I gave here is that it came to the height h, the drone came to the height h, but it is not holding the height, but somehow going down or then going up and doing it in a oscillatory fashion. So, output remains bounded, like it is going to some height capital H1 and then capital H2, in between it is oscillating, that is called marginal stability. It is like for different applications, of course, it is not very desirable thing, but the system neither grows nor dies out. So, it is called sustained oscillation. This topic will be clear in transient analysis. Okay. What is instability? Instability is that output grows without any bound. That means the drone, after reaching this height, does not stop and it keeps on increasing its altitude without bound. Okay. The system diverges and it fails to operate properly. So, if that thing happens, that is called instability. So, what is ideal? When we are giving some bounded input or bounded command, the drone will take off and will come to certain height and will hold it, because the problem is a altitude hold problem, and then it should maintain that particular height and hover. Okay. If there is some disturbance and it is shifted from that particular position, then also with due course of time it should come down to the same height, and that is called asymptotic stability. If it is coming to that particular height but oscillating, then it is called marginal stability, that is also not desirable. And finally, instability is something which we can't handle. So, this is instability is a big no. So, we have to design the control system in such a way that instability does not come, or the drone does not become unstable. Okay. So, yeah, I have already given the example of altitude control. The drone hovers at some 10 meters of height after a small wind disturbance. However, if it becomes unstable, then the drone begins to oscillate or drift uncontrollably after a small input. So, we should now understand that why stability is critical. It ensures safe and reliable operation. It prevents system damage or failure, and it is essential for drones and whatever systems we are taking into consideration. It is essential to maintain stability, and accordingly we should design the control system so that with some input command we get a desired performance out of the systems. Now, we will go through some other system specifications or performance metric. One is transient response, which will be covered in lecture. It describes how the system responds immediately after it is getting some change in the input. Okay. There is something called steady state response, the difference between desired and actual output after the system settles down for a long time. So, immediately after getting one input, the response which the system gives is called transient response, and when the system is exposed for the input for quite a bit of time and then it settles down to the input, then it gives steady state. Okay. Speed of response, how quickly the system reacts to the change in inputs. Overshoot, it is the extent to which the output exceeds the desired value. This is something which is undesirable. So, control system design should minimize overshoot. Okay. Settling time is the time taken for the output to remain within a specified tolerance band of the desired limit. Okay. Damping, how the oscillations are controlled. If the response of the system is oscillatory, then initially, then it should the oscillation should come down and the system should settle down. So, damping tells that how oscillations are being controlled. There are several damping methods like critical damping, under damping and over damping. Okay. Robustness is the ability to handle uncertainties and disturbances in the system. Sensitivity, how much the system output changes in response to variations in parameters. Okay. So, these are the desired control system specifications or performance metric which are into design considerations. When a control engineer is designing some controller, he should take care of all these performance metrics and check that whether those are in the desired limit or not. Okay. If we check the performances of a drone with this kind of performance metrics, we will see that a scenario where it should hover in a hovering stability, it should hover at a certain altitude in a stable way or altitude hold, then there should be some related performance metrics like settling time, overshoot, damping. I have already told that if it needs to hold a height h, but it is just going and coming down and oscillating, then it is a kind of undesirable behavior, and the overshoot, that means the magnitude of this exceeding the limit, should be in control. Also the oscillation should be in control. So, overshoot should be minimized, damping should be improved. Okay. Altitude tracking, steady state error. So, when it is tracking some altitude h, so when the system settles down, it should be stable at height or altitude h. Okay. Then another specification is rise time, which will be covered later. Responding to wind gusts or disturbances, robustness and transient response should be improved. Navigating a predefined path, it should follow the path accurately, and speed of response is also very important. Okay. So, these metrics help engineers to tune the controllers. As I was telling, that when the control system designer or engineer is designing the controller, he should take care of all the performance metrics, whether they are in a desired limit or not. Then these metrics ensure that systems are not just stable, but also fast, which is desirable, accurate, tracking accuracy, and also reliable. It allow performance trade-offs. That means, when we are looking for faster response, we might we have to allow some overshoot in the system, and based on the system and application, these trade-offs will come into picture. Okay. So, in this lecture we see we covered the introduction to control systems, we discussed the concept of feedback, open loop and closed loop control, mathematical representation of the systems, system responses like unit step, unit impulse, then ramp and sinusoidal responses. We did not go through all the system responses exclusively, but we have defined some of the input signals. So, in the later lectures we will go through the system responses. Okay. Then we discussed the concept of performance metrics, and we look for using these performance metrics and control system idea in drones in the later lectures. Okay. For further reading, I would suggest mathematical modeling and simulation of dynamical systems, and there are two representations of system as block diagram and signal flow graph. I would suggest these two topics to be read from this reference books. Those topics are discussed in great intricate details in all these books. Thank you.